Talk now. Okay, good, good. 3-minute warning. Yeah.
I still have one blue one left over. I'll let them know what size it is. These came by. This is yeah, there's something weird where it sort of cycles through files.
No. Deep space blue. There is a blue that is not black. That we call the idea being that space is kind of ionized. So it's not totally dark. Even when it's
Well, okay.
Anyway, black is one of my favorite colors.
Okay. That's good. That's good. Very nice. Very pretty. I like this red. It doesn't show up on the original. It was kind of dark.
All right. Thank you, sir. Thank you very much.
Yeah. I want to see if Brad can show these because he can set his up. These are the big ones. Broadcast right into the hangout. But that's the two of these. The largest ones are. These are
Okay. Yeah. If you get a T-shirt, put it on, because in the beginning of the presentation, I'll ask everybody to step up and show off the T-shirt as a group. Okay, shall we?
We are ready.
Okay.
I think we're ready. We are online.
Okay. All right. Okay, everybody. This is Silicon Valley Fourth Interest Group. This is our August meeting.
Who are you?
I'm CH Ting. Right there. Okay. Since Brad got the new T-shirt this morning, so I'm asking everybody who has the T-shirt, old or new, come up and take a picture. Not that picture, just show off. Let's line up in front to show everybody our new T-shirt. Okay.
Everybody.
Do you get everybody? Okay.
Wow.
if we stand on the table.
Okay. Great. Okay. This is our group, and
Brad and Andreas.
that's all right. That's all right. We'll just move around.
And,
Okay. Thank you very much.
Show what's on the back too.
Yeah.
the show on the front. There's some folks that have really ornate back prints.
Okay.
We're good.
Yeah. All right. Thank you so much. Thank you, Brad. And the T-shirt is $15. If you want one, try to get to contact Brad to see if you can get it, or just come up next month to get your T-shirt.
If there are any left.
All right. Okay, this morning, my topic is building spectrometer. Okay, why spectrometer in this FIG group? Some code is actually written in Forth. Okay, so I'm going to just talk about this thing in general and some specific things that I've done over the last month. Okay, so I was trained as a spectroscopist at University of Chicago long time ago.
Oh, you know you were from Chicago.
Yes. Okay, so spectroscopy. Spectroscopy, there's lots of things, lots of terms. So the earliest term is spectroscope. And this is a visual instrument that you can observe the spectrum visually through some lens and a prism, I think. And then later, people get more sophisticated, and they improve the resolution. And then, if you improve the resolution, the density of each line gets weaker. So you need to spend more time observing. And after the photographs were invented, people just use photographs to record high-resolution spectrum. And the instrument which use the film to record the spectrum is called spectroscope, spectrograph. And now everything's turned electronic. So photograph film is old-fashioned. I don't think you can buy them very conveniently nowadays. Everything's electronic. So if you use an electronic device to record the spectrum, then it's a spectrometer. Okay, so everything's done electronically. Once you have the spectrum recorded in electronic form, then you can manipulate it, you can process it all by digital technology. And so a spectrometer basically, nowadays, you have a sensor, you have a digital camera, and this digital camera can record the spectrum, and you can display the spectrum instead of on a photographic film. You can display it electronically on your computer, and if you really want it, you can print it out on paper. And now, if a spectrometer, if you can improve on the electronics and actually record the spectrum very accurately, and then display the data in some graphic form, then it's becoming a spectrophotometer. And spectrophotometer is basically concerned with the intensity. When you want to measure the intensity of each line, then you need a more sophisticated instrument to do that. So that's spectrophotometer. So I've I think it was last year. I was reading the. I don't know what I was doing, but come to this article about on the YouTube about a CD spectroscope, and the guy claimed that spectrometer is very expensive. Spectrograph is extremely a good one are very expensive because you need very expensive grating and very large mirrors to do the optics. So, you know, generally spectroscopy is out of reach for most ordinary folks. But this, this article, especially, I think MIT, one of the people in MIT actually showed that, yeah, you can build a spectroscope very cheaply with a CD, okay? Because the grating is the most expensive part of a spectrometer. But the CD-ROM are actually very nice gratings. Okay, they are curved, but they are nice gratings. Okay, and since the technology has matured, so the precision on these grooves are very high. Okay, and so with this CD-ROM, you can actually build a fairly good spectroscope. How to do it? You know, basically, you break up a piece of CD-ROM, okay, and then you use a piece of tape. Then you use a piece of masking tape and tape it over the back side of the CD, and you peel it off. Okay, and you get yourself a very nice, very cheap, but a very nice grating.
Does it matter what's been recorded?
It doesn't matter what's being recorded, as far as we can tell. Okay. Yeah, a blank one or a music CD, anything would do. Okay.
Steady 440 hertz tones.
Oh, well, 440 turn into 440 millimicrons. Okay. Yes.
Do you know what the number of lines per millimeter there are on a CD?
I don't have the numbers, but this remember, use the CD. Don't use DVD. Okay, CD is okay. DVD is not. Okay, DVD the grooves are twice closer, so the dispersion is twice bigger. And to observe the visible spectrum, the DVD disperses too far out of your view. Yes?
The web alleges that CDs, a 3.95 gigabyte DVD-R has a track pitch of 1250 lines per millimeter. A 4.7 gigabyte DVD-R has a pitch of 1351.
Yes.
Okay. Okay.
Very good ratings.
Yeah.
CDs are 625 lines per millimeter.
Okay. Well, whatever. But that's good. Okay. That's adequate and actually very good. I was not able to determine the limit of resolution of these CDs because my instrumentation is not that good. Okay, so this is a CD spectroscope. Okay, you stick this piece of CD here, and on the other side you cut a slot. Okay, and this is the spectroscope. What you do is you look through it. You can see the slit, and turn your eye about 20-30 degrees to the left, to the right, and you can see the spectrum. Okay, you just use this in phase light source, and then over to the right, you will see lights being dispersed. So this is a very, very nice spectrograph. Okay, very cheap. Okay, but you want a better resolution, you just use a bigger box. Okay, so here, this is one of my spectrographs. Okay, so here I have a piece of CD there, and if you just aim this thing to the source of the light, and you look through, you see the slot, and turn about 30 degrees, 20 degrees, you can see the spectrum. And because it's longer, so you get a better resolution.
So that's a 30-degree pipe band on there.
Yeah, right. Yeah, this is I think a 22.5 degree pipe angle. So it's a nice one. Okay, that's a spectroscope. Spectroscope, basically you use your eyeball as the sensor and the detector. Here are a whole bunch of them. So spectrograph. If you spectrographs are spectra recorded on photographic plates. Modern digital cameras have millions of pixels and are capable of recording good spectrographs. Digital spectrographs still need development. Okay, so in here, if you have take this piece of CD-ROM out and put the CD-ROM, stick it in front of your lens. Okay, and this way you have your spectrograph, and you have the camera there, and aiming about 20 degrees from the slit, and you can actually take photographs of the spectrum. Okay, and the digital camera is extreme nowadays. You got 20 megapixels in one picture, so the resolution, as far as the camera is concerned, resolution is really good, much better than the photographic films in the old days. So, but digital photographs still need development. You take a picture, and then you have to somehow transfer the picture into your computer to visualize it. Okay, so that's just like a photograph. You have to develop it, and then you can look at it. Yes.
Unlike regular film that has like splotches of chemicals, the digital elements are all in lines. Do they interfere with the data that's coming in from the spectral material?
No. I think they have and the modern design of digital camera. In front of each pixel, there's going to be filters to black, and I mean the red, green, and blue filters. Okay. So they use three filters to separate the color, and then but the color separation is very low resolution. Okay, the camera has a much higher resolution, but the sensors, some sensors, they have different designs. They have 1 pixel for red, 1 pixel for green, and I mean generally 1 pixel of red, 1 pixel of blue, and 2 pixels of green. Okay, so you got the 4 pixels for each element, and there are filters in front of each element. So they may cut down the light. Okay, preferably you want a sensor without filters, without color filters.
The old days it had the prism, and you would have three sensors.
Yeah. So here, these are the when you take a photograph, you still have to process it, move the image in a form that you can actually work on. So here is my spectrograph. My camera is down there. I was trying to take the spectrum of the sun. So this is the camera there. So CD spectroscopy, CD-ROM has very high, very accurate ruling and can be used as precision grading for spectroscopy. So this is the most expensive part of a spectroscope. Digital cameras are very sensitive and accurate area detectors for spectrographs and for spectrometer. The only drawback in CD spectroscopy is that the spectrum lines are curved, okay? Because I really want these grooves to be parallel, okay? But they are curved.
Does it matter how much of the arc of the CD you have? If I wanted it to be less curved, I would only take a narrow strip.
From the outside.
From the outside, yeah.
Yes.
Yes, the reason is to do spectroscopy, you're going to need a rather large grating because you need the energy, the light coming in. Because when you spread it out, that means your exposure time has to go up because now everything's all spread out. But
Yeah.
yes, in this case, you probably would like to have more.
Right. You want a larger grating, and when you have larger grating, you need larger optics to match it. And all these things are optimization.
Maybe 12-inch long planes. Just get the linear ones.
Yeah, the linear one will be expensive. Okay. So because the grooves are circular, so the spectrum is circular. Okay. So you take a photograph. If you look at it, let me see. I think I have some. Okay, here is a spectrum of a Mercury.
Wow, the planet. The planet Mercury?
No, not the element. Oh, the Mercury element. Okay, this is a Mercury discharge lamp. I think I didn't bring it. In the old days when you try to erase UV erasable ROM, you use the Mercury lamp. You don't see the UV. That's correct. The UV is over here, but it's the grating absorbs UV, so you don't have it. You can see it, right? So the interesting thing about the Mercury discharge lamp is that it is a very efficient light source, but most of the energy is concentrated in the deep UV. 253 millimicrons. Okay.
Nanometers.
Nanometers. Yeah, that's right. The nanometers. Or 2,537 angstroms.
Yes.
Okay.
The Earth's atmosphere.
Absorbs it. Yeah.
320
Yeah, that's right. So most of the energy is out there in the UV. But a few lines showed up at a very much less density. So, to erase UV erasable ROM, you need that deep UV. That's why we have those discharge lamp. But for visible applications, if you want to build a fluorescent light, then you have phosphors to absorb ultraviolet light and re-emit visible light, and that's how most of the fluorescent lab is. But this is very interesting. This doublet is about 20 angstroms, or 20 angstroms, or 2 microns, or 2.2 microns. 20 angstroms. Okay, 2 nanometers. So these two lines are 20 angstroms apart. So you can see the spectrograph, the CD, can resolve these 2 lines very comfortably. And from these 2 lines, you can estimate that the resolution is in the neighborhood of 1 angstrom. Okay, so the CD-ROM is capable of resolving down to 1 angstrom resolution. So that's very nice. But the problem is that it's curved. Okay, and if you want to do anything with this, you have to straighten out these curves. Okay. Okay, this is the spectrum of this compact fluorescent light, and it's a long history of spectroscopy. Okay, finally we arrive at this. This is the most efficient visible lamp so far. Okay, I think the next step, of course, is the LED. Yeah, but you know, besides LED lamps, this is the most efficient one. And the interesting thing is that these phosphors are 2 rare earth salts. Okay, and the turbine element produce these 3 lines, and the European produce the red light. Okay, so this compact fluorescent light looks very very cheap, very you know, nothing very ordinary, because there are so many of them. But the science behind it is extremely interesting. And these rare earth elements produce very sharp lines. Okay. And you know, spectroscopy, what the spectroscopists are interested are these very sharp lines. You get lots of sharp lines, and you have lots of information, and you can write lots of paper on each and every one of these lines. Yes.
You notice how they look kind of blurred together?
Oh yeah, yeah.
That's because the phosphor is very close together. Okay. Now, have you had a gas?
No. This is I was taking this one with my video my video camera. The video camera. I wasn't able to focus it very well. Okay, and it's out of focus. Okay, so the blur is not. Now, if I use a better one, I use this camera instead of the video recorder, and actually focus it properly. You get this kind of spectrum, and these 2 lines are very well defined, but they are curved. Okay.
See?
Yes.
That doublet's more in the yellow to the eye. So is your camera greening it up a bit?
No, no, no. I think it is pretty much this, the original color. Okay. If you look through scope, you can see it's green. It's very green, and the yellow, the yellow color. If you got that better resolution, more intensity. Yeah. Sorry. You will see this part is more to the yellow than green. But this is overexposed, so the color cannot blend that all over.
That's why that other yellow in there.
It's just overexposure. Yeah, and the camera kind of overexposure, and it seeps into the green pixels. Okay. So this is a very bad picture, but it's using a video recorder. Basically, you can take a very nice photographs through the spectrograph. Okay, spectrometer. Now we have the picture in electronic form. Okay, it's just that this electronic image data are not very easily accessible to us. Electronic image recorded by digital camera can be processed to become a spectrometer. But you would like to be able to process the image real time. So right now, this kind of camera does not give you it has all the information. It even has the Wi-Fi link that you can control it. But it's still a camera, okay? A camera is to take a picture, and the picture is stored there, and then later on you can look at and do things about it. So we still have, I would like to be able to control the camera, the digital camera interactively, to do the focusing, to do the exposure, and all this control stuff. But right now we don't. The camera has all the function there, but it's just not. I'm not able to access all the functions through a USB cable, for example. And the curved spectral line must be straightened because we want to integrate. We want to integrate it and process the image. And the most important thing is to straighten these lines. And the straightened spectral lines can be integrated vertically to form accurate spectrum. So that's the spectrum is actually spread out in 2 dimensions. And we only need the information we need is a 1-dimensional spectrum. And we could integrate all the related pixels into a single cell. Okay. So this is if you want to make a spectrometer, right now I have a Spectrograph. Okay, I got a picture there, and I have to do things on the picture separately. But if I can access the data directly, then it's going to be a spectrometer.
So
Yes.
Is there a way to calibrate not by color, by the distance?
Oh yes.
In
Oh yes.
other words, is there an element that makes lines that are so precisely spaced in 200 nanometers apart that you could actually calibrate?
Yes, there is.
Exactly.
What substance is that?
Iron.
Iron?
Yeah.
Iron
Exactly.
and thorium argon are used for generating the laboratory lines.
Okay, that's like test bars.
Yeah, that's right.
Yes, well, it's not so much, in astronomy, it's not so much, what it does is we need to know where the spectral lines are at rest.
Right. Yeah.
So that when you look at, say, the star and you see absorption lines, you say, okay, how much of it did it shift due to Doppler? Is the object we're looking at coming toward us or away from us? So they can measure rate of velocity.
Yeah.
But yes, those are the 2 main things they use.
Iron and thorium?
Yeah, they're an iron lamp
ion, ion arc.
Okay.
You have two electrode arc. Okay, the arc spectrum. Actually, to be a student spectroscopy, student of spectroscopy, the first thing I have to learn is to read the ion spectrum. Okay, ion spectrum is spreading out very, very densely, lots of lines, very sharp lines, and you just have to read, be able to read the ion spectrum, and then you know exactly.
So you can make a ruler out of that, sort of.
Yeah. The ion spectrum is actually a very nice ruler, but you have to be able to read it.
Read that, those lines.
Because there are patterns.
Yeah, you know what the wavelength those lines are at. They're usually very sharp, because in astronomy, sometimes these lines we look at can be very broad. Okay? So what you do is you're able then to use interpolation to figure out what the wavelength of the line in question is.
Yeah, there are so many ion lines that are so dense that you don't even need to interpolate, because usually there's a line very close to what the spectra you are looking at. Okay, so that's the but all these things can be calibrated. Okay, and if you got it calibrated, then you know exactly what the wavelengths of. Okay, so the spectral lines are curved. How do you straighten them out? Okay, and the basic assumption is that I have to assume that the spectral lines are concentric circles. Okay, and this I don't have any theoretical way of knowing that they are actually precisely concentric. They may be ellipses, okay? But we just assume they are circles. And if for a very sharp spectral line, you take 3 points on the spectral line, and you can determine the center of the circle. And I have to assume that all the lines are from the same circle, okay? I don't know, okay? But I assume it. But it looks like they are concentric, okay? Because you look at the spectrum, if you turn things around, you can see really big arcs. And they don't look like ellipses. They look like circular. So, but this is my this is just my assumption. But this is the first step. Okay, whatever, if they're concentric or they have different radius of different lengths, I don't know. But we can determine all this. Okay, take a spectrum, take 3 points, use a very sharp line, take 3 points of it, and then from these 3 points you can determine the center of this circle. Okay, and 3 points on a circle. So we have A, B, and C, and actually we have 2 lines, AB and BC. And the equation of AB is there, equation of the BC is there. They most likely have different slopes. Okay. And so here is a picture. You have A, B, and C, and you connect A and B, connect B and C, and you know the bisector line. You can calculate that. So you have 2 lines perpendicular, a line perpendicular to this one, and passes through the center of this line. And this is one of the radius of the circle. And you can have the same thing for the A and B, and find out another line which goes through the center. And the point where these two lines intersect, that's the center of the circle. So this is what you want to find. And once you find the center of the circle, assuming all the lines have the same center, and you can determine and plot out all these circles, and you just find out each pixels on the circle, and that's they are all of the same wavelength, and you can sum them up to form a very accurate spectrum. So M1, M2, these are the radius. And the equation of this, the interesting thing, because this M1 is perpendicular to AB, the line AB. And the slope of M1 is the slope of AB inverted and negated. Okay, so this is the perpendicular, the line which perpendicular, the line perpendicular to the line AB. And then it has to, this line has to pass through the center of A and B. So the A3 is the center of the Y and center of the X, and then scaled by H1. The same thing for the M2. So we have these two equations, okay. And these two equations, when the X and Y are at the center, the X and Y has to satisfy these two equations, and you can find X and Y of the center. Right?
Correct.
Okay, thank you. Okay, if the R is the center at the intersect of M3 and M4, so we have these two equations, and the Y4 and X4 must satisfy these two equations. And if you solve them, you can solve X4 and you can solve Y4. And the calculation, when you want to have the angles of lines, generally you use tangent, cotangent, and all these transcendental functions, and you need a big computer to do all these things. But if you analyze this thing very thoroughly, only multiplication and division, add and subtract are required, and all these numbers can be integers. Okay. So the calculation is not. It is. You can do very precise computations without the floating points. So the center. To calculate the center, you have to solve these four equations, and I use a spreadsheet to do the calculation, just so I don't have to, do all the calculation by hand. And there are so many things, so many variables involved. My mind is not good enough to keep track of all these variables. But a spreadsheet is ideal for keeping track of everything. So let me show you this, the spreadsheet. Yeah. So this is the spreadsheet that I use to do the calculation. Okay. So I have x1, y1, x2, y2, x3, y3. These are the 3 points. Okay. And then I can calculate M3 and M4, the slope. M3 is the invert of H1 negated. Okay. So these are very easy to do the to do the calculation with spreadsheet, but each cell can refer to other cells. Okay, and the nicest thing, so I got the N3 and N4. Okay, there, and X21, that's the midpoint of X1 and X2, and Y21 is midpoint of Y2 and Y1, and X32, Y32. So I get M3, M4, and the midpoint of them, and then I can just go calculate the X and Y of the center. Okay, so you nice thing about spreadsheet is that each row you can have a different arc. Okay, and you fill in just filled in the X1, Y1, X2, Y2, X3, Y3, and boom, I got everything calculated. Okay, and to check if I do the computation correctly, then the correct is I can calculate the radius, the radius at X1 and the A, B, and C. And so these last three columns are the calculations. Once I got X and Y, the center of the circle, okay, then I just calculate X1 and Y1. You can calculate the radius. And then the B point and the C point, they came out exactly the same. I was kind of surprised. I think at least they're changing a last digit or something, but they came up good to the last digit.
Because they're pixels. You actually, these numbers are pixels on your screen.
These are pixels on the screen. So these are pixels. They are digit. They are integers. Okay, yeah. But the spreadsheet goes through the floating point calculations. So actually, when you get these are actually floating point numbers, but they match exactly. So I was kind of very happy. Yeah. And then I just do one measurement, make 3 points, and then fill in this, and everything came out very nicely. Any comments? Any questions?
Yeah, I'm starting to blur a little numbers. Could we get, instead of a CD, could we just get like a wire or something and just vibrate it really fast?
No. Then you just create more problem for yourself.
What other cheap material is straight rather than curved? Is there any other cheap spectral material that
well, I mean, I think we used to
take polishing sandpaper and scrape on a shiny material, and there was a way of making a hologram of and made it appear three-dimensional by essentially making yourself a spectral what do you call it, a grating out of just by, you could do it with an eraser or something like that.
Well, you can.
No, you really need to have
high accuracy.
Very high accurate, yes. That's why these gradings are
Yeah.
like thousands per millimeter.
Yeah, you see, this we have there are optical ways you can use the use optical distortions of lenses, and generally if you use lenses, the image a straight line usually get curved. Okay, so if you kind of use the system in the opposite way, you can actually distort the thing the other way. Okay, so there are physical methods or optical methods to straighten a line. Okay, but once you have data in digital form, use the computer, right? Yeah, it's the best way.
Another method for having a grading, I think, is to use fiber optic, where you have you have one fiber optic coming in, and then these other ones that branch off, but their size varies by a specific increment. So that when the light comes in, you'll get light coming out, but at different times, so you get that. You get the interference pattern.
It's going to be much more expensive, even compared to a grating. Okay, so don't think about these things. You know, CD-ROM. That's the way to go. Okay, they are making millions and millions of them all the time, and the precision is so good that except it's curved. Yes.
So curve is from CD-ROM because we are using CD-ROM, so we get curve.
Yes.
It's not from object.
No. But even if you have the best designed spectrograph, okay, you still go through mirrors, okay, the curved mirrors, and these things distorted the spectrum. So yeah, if you look carefully, even the best spectrograph, the lines are slightly curved, okay. Mm-hmm.
So let's just Google spectral camera or something. And just give me the image. I can see get the straight line and curve.
Yeah. I think there's optical ways to correct it, and there are also mathematical ways to correct it. Okay, so you know, now I can find the circles, or I can find the center of the center of these circles. Okay. So I use the spreadsheet to calculate the center. And now, how do you straighten out these curved lines? Okay. What I did was you scan from the top of the spectrum. Okay. You draw a circle. Okay. Scan from the top in the spectrograph. For each pixel, draw a circle over the. You know, you have a square, a rectangle spectrograph. Scan the top of line. Each line you draw a circle. Okay. With the radius you just calculate it. For each pixel, draw a circle over the spectrograph. And then from this curve, you read the pixels on the circle, and then you store them in a vertical line. Okay? And this way you go through a circle and then produce a straight line. So this is how I straighten it out. So read each pixel on a circle and store it in the corresponding pixel in a vertical column. And if you like, you can sum up while you read the circles, you can sum up all the intensity of the pixels into a single cell. And that you build up a single line spectrum at very high precision. Okay. Can you see the circles?
Yes.
Okay. You know, so I from here, from any spectrum, I just take this one most prominent line and get the x1, x2, and x3, and calculate the circle. And once I have, so you know, the center of the circle is probably over here, okay? And then on top of each line, I can draw a circle, okay? And if the calculation is correct, or my assumption is correct, that all the circles are concentric from the same center, then these lines should overlay on each spectrum line, okay? And so this way you can straighten up curved lines into a straight spectrum.
A CD is not a spiral.
Mm-hmm.
It doesn't spiral like an old record.
I think it is spiral. It is spiral. It's spiral.
Is this spiral?
Yeah, it's spiral. It's continuous. it's spiral. But that's what that's how you can run the whole CD, just spin it. Yeah, and it's I don't know. Okay. But I think it is. They are not perfect. It's perfect enough. Because because the lines are spaced so closely, you cannot distinguish it from a spiral from a circles.
Channels we're using for spectroscopy is to channel light, so that even if you're a little bit off, you hit. It's a separation that matters. Anywhere in the channel, you hit that data right at the bottom.
Yeah, right,
so
right.
It's a lucky thing for us. It's such a fine grain that we can use it for.
Yeah, that's right. Yeah. But the diffraction, the diffraction is that, the same light goes into the same direction. That's the grating. And practically, don't worry about the details, circular or spiral. It looks like circles, okay? And if I draw the circles, they match pretty well, okay? I'll show you the discrepancy later. Okay, to draw the circle. If let's assume we are just have a circle in the first quadrant, the line can cover probably 2 quadrants. For point x, y on the circle of a radius, you start from the top or anywhere. You calculated the square of x and y, the sum of x and y. So that's a square. Generally, if you want the radius, you take a square root. But why take the square root? You don't need the square root, because what we want to do is the deviation from this radius, or the square of the radius. Okay. So from the top, you move y to y minus 1. Then RR is reduced by to RR minus 2y plus 1. Okay, you step one pixel down, and then you reduce RR by 2y minus 1. Okay, and then you move x, you increase x to x plus 1. And when you increase x to x plus 1, the RR would have to add 2x plus 1 to it. So this is a square, n plus 1 square is equal to n square plus 2n plus 1, right? So this is all from that basic formula. So you just move x until RR is greater than the first one you calculated, and you back off by 1. So this way you can find the x and y closest to the circle. Okay, and the calculation is very. If you forget about the radius, don't do the square root. Okay, just accumulate and correct the numbers of the square of x plus square of y, and you can follow the circle very precisely. As precise as you can with that digital grid. Okay. So you increment x until RR is greater than the original RR0. Then reduce it by 1. Now xy is always inside the circle, but the closest to that circle. Okay. So the calculation can be done very efficiently with integers. Okay, you don't need the floating point or anything. And this is the result. The lines are straightened out because remember the curves. I'm just following the circle, and then put the pixels in a straight column. Okay. The other picture, you see, I cannot see if these are not straight or not parallel. Okay, so the following the circle, you can find out the spectral lines and put them vertically. Any question? Yeah.
You're basically doing exactly the same thing for a different type of spectrograph known as a shell spectrograph.
Okay.
Because with your spectrograph, if you want to go to higher and higher resolution, well, the length gets longer and longer and longer. Well, so what it does is it just breaks it up into, well, a shell means bladder in French. So you get these little chunks and you just put them one underneath another. The thing is, they're curved.
Yeah.
And you're doing the same thing there to straighten them out.
Yeah, that's right. Okay, so the assumption is that all these spectral lines are on concentric circles. Okay, so if you follow that assumption, the result looks like pretty good. Okay, but it's okay if you sum up each lines, and you see this one is the blue line, and then the cyan broad line is over here, and this one is the green line. You can see there are two lines, something beneath. So these are the two green lines, and then here these are the yellow lines. They're a little bit broader. Okay, and this is the red peak. Okay, so this is the this is a spectrograph. Okay, or when it is all electronically, it's a spectrometer. It's whatever. Okay, but if I just take one pixel, one line of the spectrum, and then plot it, it's a bit noisy because you don't get enough light. Each pixel, the data is limited. Okay, and in the digital camera, all the pixels, or I don't know what the actual cells, actual sensor in the camera, how it does, but when the camera process the image and report it to me digitally, it is in the JPEG form. But you can convert that JPEG form into a bitmap. So I'm converting the and in the camera you can actually record raw pixels. Okay, but generally that takes too much memory space. So generally the camera processes the image and present to you in JPEG or some other compressed form. But that form you can turn it, reformat it into bitmap, a BMP format, because BMP format I can read the file. The BMP file, the format is standard, so you can go read all the pixels, and each pixel has 1 byte, 256 bit, red, green, and blue. So what I'm doing, I don't care about red, green, and blue because my resolution is much better than the color sensor. So I just take the red pixel, green pixel, and blue pixel and sum them together. That may not be the right way to do, but just sum them together, you get one pixel value, and then you can sum all these pixels over the line. But without summing up the line, I just read one line, and then you can see there's some noise in it, but the resolution is much higher. So the line is actually much narrow. Okay, so this is what the camera can do. Okay, and when I sum things up, I lost resolution. Okay, I lost resolution, but I gain in accuracy. Okay, so this is the trade-off. But the loss of resolution is one of the most important factor is that the line was not straightened enough. Okay, so I'm not summing up at the exact circle, and it waved a little bit, so I get a couple lines together, and the resolution suffered. So.
Are you sampling the image though? Like, are you doing it sort of at integer pixel?
Well, you know, it's I got the whole image in BMP format, so I just take one row of data. Okay. Yes.
When you take your base data,
yes.
and you JPEG it, you throw away a significant amount of information.
Oh yes. Oh yes. Yes.
Is there a reason why you want to do that? I mean, if you're looking for some accuracy, rather than trying to get it back by lots of calculations, you've got the raw data. Yeah, it's 10 million pixels or 12 million.
Yeah. Right.
But you've got a computer.
Mm-hmm.
You don't
Yeah. Right. That's right.
So I would think that you would just take the raw data and then process that.
Yeah.
Be much more.
Yes. These are all the the details. If you really want all the data, yeah, why not take the raw data? But it's more convenient for me right now. Just take whatever the form that is spit out, and turn it into BMP and process it. Because I think from these things you can see the resolution is not a problem. The problem is my processing. Okay.
Do you have much more?
I'm almost done.
Your thing here, JPEG, you can change it. So I believe you can, so that it can be lossless. Yes.
Yeah.
Yeah, but you'd have to figure out what that is.
It's a variable.
Oh.
JPEG spec.
Yeah, it's a function of whatever is using. Can we? Take this up at lunch?
Let's finish this thing. Yes.
Real quick.
Yes.
You could use something called FITS. FITS. That's an astronomical one where you can actually take, they use it for CCD and will do as raw.
Yeah. Actually, the camera can take a picture raw. Okay. But I'm not using it in the raw mode. So I'm getting the JPEG data out. But I can turn the JPEG into BMP, no problem. But if I can get the BMP to begin with, it's much better. So the spectrometer, you can do actually accurate measurement of spectral lines, intensity for quantitative analysis of atom and molecules. So once we have a spectrometer, photometer is just another software layer. So you just sum up everything and get the intensity more accurate than if you just scan one line. Okay, but digital camera, now as I have it, is no spectrometer yet. To make a spectrometer, I need intimate control of the camera, the focal length, the aperture, the exposure, and instant downloading image. So I need to be able to get the image and see what's going on. Yes.
What do you mean by instant download?
I hook it up, and I see the picture on my camera, and I move anything, the picture moves.
Okay, because you remember there is a certain readout time for CCD.
That I don't mind. Okay. 1 second delay, that's no problem. 1 minute delay, I can suffer. Yeah. Okay, let's go down. And right now, I'm reading USB 3. The new standard has the camera interface. That will allow these capabilities. You can interactively control the camera. But they are not yet available commercially. I think there are some very digital microscopes. They use this technology. Okay, so you can look at things and actually change things interactively. I'm waiting for that, but for the time being, I have plenty of time. Okay, I don't need any real-time stuff. And what I'm trying to solve is the physical problem. If I can solve, then I can improve them later.
You know, my ongoing project porting G-Forth to an RTOS, because RTOSs, a lot of RTOSs now have USB interface drivers for them. And I think that would be very helpful for you if I could come up with something like that. If I
Okay.
find time enough to work hard
All right.
enough so that I can retire and not be a slave to money.
Oh, well, you still have to do.
Let's thank the speaker.
Okay, thank you so much. All right, we'll go lunch. So see you in the afternoon. Bye-bye.